Tutorial 4. So we run through this tutorial, we run through a lot of the intuition behind this and some of the ideas. We'll now run through how to attack question 3 on weighted least squares. So you've got a regression. So you've got the start, so there should be a little I here to keep it all consistent. So we've got a regression of y, and we've got k variables and an intercept, so it's just a standard linear model with a disturbance term u. So assume that the form of the heteroscedasticity is known up to a multiplicative constant hi, namely this. So that's just this in words. Xi, it's written, I mean a lot of these things aren't defined. The xi bold here refers to all x j I for all I equals 1, 2. Again, it's not misstated the sample size. So again, some of these questions should give more. I think it's maybe taking it from the lecture. I'm not, but there's again, this here is saying I've got a sample. Say we've got from I equals 1 to t or m, whatever you want to call the sample size. I equals 1 to n, and we've got k variables here. So this capital X bar just means all the sample data on the characteristics x. Hi is then some function, and again it's saying that we know what that is. So in this particular, it could be anything. So this just means then the conditional variance of the disturbance given the personal characteristics of person I are, well no sorry, this capital Xi in this case instance is just for person. It should be for all x, in which case that would be correct. So we'll do it like this. And it's then assuming it's just a function of person's i's characteristic in this particular example. So this just says the variance of ui, the disturbance of person I, given all the personal characteristics in the sample, is equal to a constant times some function of the characteristics of person I. So that's all that's saying. So this is assuming that this is known to us. So for example, it might be the exponential. Sometimes this is a common xi, but this is going to be all some linear function of all the x's here. So that's an example there, and it could be anything. But the point is, in this example, they're assuming it's known. So this h function is known. Let's use this information to derive a homoscedastic version of the above equation. What is the main limitation of the WS technique for correcting? Okay, so I mean, it's a bit, so what it's, in essence, it's saying how can we transform this regression to make such the Gauss-Markov Theorem holds? Or in essence, how do we do weighted least squares? It's been a little bit unclear. Like, it's asking you, in essence, to come up with a method which will allow us to derive efficient estimation when applying least squares to this regression problem. That's what it's asking. How can you do that? Then it's asking what is the main limitation of this WLS technique for correcting for heteroscedasticity. So we'll do let's just write it all out again. So again, these questions could benefit from a bit more. We've got yi equals, and in general we've got alpha dash xi. Just writing this in its matrix, in its vector form. This is just equivalent. We'll expand it all out to this before. So we're just stacking it all. This part's actually relevant for the question anyway. We're not so much interested in the linear bit. This alpha dash naught xi, when you expand it all out, it's just going to be, let's call it alpha dash xi. It's just going to be a constant plus alpha 1 x1i plus, it's just a way of succinctly writing it in its vector form. So you sometimes see it written like this. We've got a sample, again it should really say from I equals 1 to n. And so it's asking us, what it's getting at here is how can we transform this regression such that the Gauss-Markov conditions hold. So again, it should really give you all the assumptions. So again, we've already assumed linear in parameters. So that's the key assumption of Gauss-Markov. We've also got to assume no perfect multiple linearity. In essence, we've got no linearly redundant combination of variables. So for example, including the same variable twice. And the crucial bit then finally is that we've got the expectation of the disturbance given all the personal characteristics in the sample equals naught for all people and for all characteristics x. So we've got this zero conditional mean. These three things imply alpha hat OLS is unbiased. So when we talk about efficiency and we talk about Gauss-Markov and weighted least squares, we like to assume then that it's unbiased, that all the conditions hold for unbiasedness, and then we're just looking at the extra conditions for which we can then get efficiency on top of the unbiasedness. So in that particular, this just means E of the alpha hat OLS equals alpha, the true coefficient. And you've proven this result. We did a video clip on this. We proved this in tutorial 2 for the case of for the case of an intercept and one regressor. So you've already proven this result already. Assuming this then, the extra two conditions then for OLS to be best linear unbiased is that the variance of UI given all x is a constant for all people I and all characteristics x. And one we've not focused on really so much, but technically we also need that the disturbances of the different people are uncorrelated for all different people and x. So we've just been maintaining this. Implicitly you're maintaining this. So if this holds, the only thing that we need then left for the Gauss-Markov is this. So we've got 5 conditions. We've got Gauss-Markov 1, Gauss-Markov 3, they give you the unbiasedness, and then Gauss-Markov 4 and Gauss-Markov 5. These 5 conditions hold. This implies alpha hat OLS is blue, best linear unbiased. Namely, it's got the smallest variant relative to any other estimator that's linear in the y's that is unbiased. And so that's the result, is that these conditions hold. So these, once you've got unbiasedness from here, these extra 2 conditions then are the key parts for efficiency. You don't need these for unbiasedness. These are the extra conditions needed for OLS to be efficient. So we're always maintaining this one, so we're going to forget about this. We'll always assume that holds. So then everything then that assuming that if GM1, GM2, GM3 and GM5 all hold, all that's left then to establish is whether or not this homoscedasticity assumption holds. And remember, the reason why OLS is efficient when that holds under all these other conditions, and we went through this in depth, is because remember what OLS does, it's the parameter that minimizes the sum of squared residuals, yi alpha dash xi squared 1 over n. The 1 over n, you don't have to put the 1 over n, but we often write it in this way. Namely, the minimizer of this will not change when you multiply it by a positive constant. So OLS is the minimizer of the sum of squared residuals. And what you can think is that, well, what's going on is that when you fit this line to a set of points, you're giving equal weight to each point in the sample. So think of this as kind of like a social welfare function or a loss function. You're giving equal weight to kind of each person's error, in essence, for how the line fits to their data point. So you can see then that if each point in the sample has got the same level of variability in the error, this UI is the mistake, remember. If this is the same for all people, well, the best thing you can do when you're minimizing your weight function, choosing your weights to construct this measure of loss, or how far away it fits on the line to the set of points, is to give equal weights to each point in the sample. If not, well, weighted least squares, you can generalize this OLS to do weighted least squares, where you choose some weight and you select this and you come up with a new loss function where these WIs will be selected by the researcher for I equals 1 to n. So we can see straight away weighted least squares, OLS is just a special case where the weight's a constant. For example, this we get then to OLS. So weighted least squares, well, then you can see there's an infinite number of possibilities of weights that you can give, and we normally normalise the weights to sum to 1, because again, normalising these weights to sum to 1 will not change the minimizer of this function. If you multiply this by 2 or 200 or 500, it will not change its minimizer. Well, it makes sense then that assume that if there is heteroscedasticity, variance of ui given x, call it just sigma I squared in general, it varies. Well, the optimal weights will be proportional to 1 divided by the standard error, and we actually showed this in a simple example. It makes sense as the standard error of disturbance of person I increases. Well, the noisier is the data point around the true line there, so we want to give less weight to that point in our loss function, because we don't want OLS, we don't want the least squares method to fit around that point because it's really noisy. So this implies then you want to give a lower weight to that point, and it turns out the optimal weights will be those which move proportionally like this. And that's the result. So actually, and then the reason why this works, so why this is a general result then, if you know the form of the heteroscedasticity, and this is what this question is saying, you know the form of, in essence what it's saying is you know sigma I up to a constant. So you know sigma. So in that case, so this is then the result. That intuitively it makes sense. So if all of the conditions hold for Gauss-Markov, if the heteroscedasticities of this form and it's known I equals 1 to n, well, we can just transform, we can make a new loss function using these weights and minimize this, and that's weighted least squares, and that will be best linear unbiased. And the reason is, well, just now apply it to the question. Take the regression yi equal, let's write it the way they've done it, b0 plus b1 x1i plus dot 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 bk xki plus ui, where variance ui given x is sigma squared hi, where this hi is known to us. Well, this just means that the standard error is the square root of this. So it's sigma square root hi. This is our standard error in this case, standard of the u. Well, then we need weights proportional to this. So again, we can just take the weights as 1 divided by h square root of hi. If you multiply both sides by 1 over this, so you divide both sides by square root of hi. Well, there's two ways to think about this. Now, in this new model, this is just a new regression now, where we've got yi star equals b0 times x0 star, and we'll see the link between the two intersect. x1i star plus where then, so you can see now, of course, this is just this redefined. Now we're going to regress this on a this will be 1 over square root of hi. This is this variable, and so on. So he's compared the entities here. So now this is a new regression, and we can measure all the. We're assuming that this hi is known to us, and of course we can measure y and all the x's. So therefore we can construct this new regression, and assuming all of the Gauss-Markov holds, all the other Gauss-Markov conditions hold. Well, remember the key thing for unbiasedness is that e of ui star, the new variable in our regression, satisfies the zero conditional mean. Well, we can verify that. Ui star, just plug it in, is equal to e of the original ui divided by this hi, again a function of xi, been suppressing that, but it's a function of xi, given x. Again, when we condition on x is fixed or known, so we know what x is. That's in essence, this conditioning says set x to some known value, so some values. So this is known, so it comes outside, it just becomes constant. Sorry, the square root of this. And again, by Gauss-Markov 3, we already assumed that this was not for all I in x. So this is not for all I in x. So this transform regression is still unbiased. It's still linear in parameters. It's still not going to have perfect multilinearity because there was no linearly redundant combinations of variables. So when we reweight them, they'll still be linearly independent. The errors won't be correlated again, and we've ruled that out already. So the only thing left then is to see what's happened to the variance. If the variance in this new model, transform model, is constant, then we know by the Gauss-Markov theorem, OLS applied to this new regression will be best linear unbiased. And we can verify that because, well, in this case, the variance of ui star given x, well, because the mean of ui star is not, it's just e of ui star squared given x. Because of this equals not, so we've used that to simplify it down. Plug in the ui star squared, you're going to get e of ui squared over hi xi, again square it given x. When we condition on x is fixed, so it comes out 1 over hi xi e of ui squared given x, and again this is just sigma squared hi. This is just the variance of ui, because again we've assumed the conditional mean of u given x is not, so this is just the variance of ui, which is assumed to be sigma squared hi. So we can see the hi's cancel, we're left with sigma squared for all I and x. So now when we divided both sides by 1 divided by this hi, which is proportional to the standard deviation of u, this new model, the new disturbance in our new regression, does have constant variance. So the Gauss-Markov theorem holds here. Because as I said, we've already verified, we've already assumed all the other ones, they still hold, it's still got a zero conditional mean, and we've shown now it's got a constant variance, and therefore OLS applied here has to be the best linear unbiased estimator by Gauss-Markov. And what's going on? Well, think about it this way. When we divide both sides by this, it's the same thing as doing weighted least squares, and that's why it's called weighted least squares. So it's the same thing of dividing by square root of hi. Just stack it all into its vector form again to make it easier to write. We've got divided by square root hi plus ui. Well, when we regress y divided by square root of hi and x divided by square root of hi, well now when we go to our weighted least squares, this we call yi star, remember, yi star minus alpha dash xi star squared. So again, this would be our sum of squared residuals in this new transform regression, where yi star is just yi divided by square root of hi, and xi star is just all of the regressors divided by square root of hi. Well, this here we can take out, we can see it's just equal to the sum I equals 1 to n of, well, by definition this is just yi. Again, we're going around the houses here, but we're seeing what all we're doing is it's just equivalent to reweighting the least squares function squared. So we can see the hi is going to come out. This is the original. This is the original residual squared. Now we've attached these weights, so we can see it's equivalent. Dividing both sides of the equation by 1 over the square root of hi is the same as reweighting and giving the weight moving proportionally to something that goes with the variance of the ui. So this now hi bigger means variance of u bigger, and it's giving less weight. So multiplying both sides of the equation by 1 divided by square root of hi, something that's proportional to the standard deviation to the variance of ui given x, is the same. This would then be, when we do OLS applied to this new regression, well, this is just OLS applied to the new regression of yi star and xi star. Again, OLS applies equal weight to each point in the sample, 1 over n. So again, that we normally put this outside. It's got equal weight to each point in the sample. This is just the same as doing the original regression y and x and applying these weights. So that's why it's called weighted least squares, and that's why multiplying both sides by 1 over square root hi will give us an unbiased, give us a consistent estimate. You can see it by the Gauss-Markov theorem, and you can also see what's going on. It's attaching weights. When we do the least squares minimization, you're giving optimal weights. You're choosing the weights to move inversely with the variance of u. So that's the key bit then. So the next part is, what are the downsides to weighted least squares? Well, the biggest downside, in this question it says hi is known. So of course it's not an issue for this question. But more broadly, hi will not be known, namely the variance of ui given x. In general, is just going to be whatever sigma I squared, and this could be anything, some function of x. I mean, we don't know what it is. So when it's unknown, one of the problems is we've got to try and estimate this, and therefore this can, and there are methods to do that. But the downside is in practice, in this question doesn't apply. But when in general, when it's not known, we don't know the form of the heteroscedasticity. Thinking complex examples, it's not clear how the variance of the disturbance moves with people's characteristics. It could be 10 or 20 characteristics. So there'd be no way of just knowing what the model was in general for the variance. So you have to estimate, in practice you've got to estimate these. So that can, of course, it means it will not be efficient in small samples. It becomes a large sample result. So in small samples, it's not necessarily clear that using weighted least squares will be an improvement in efficiency, because you've got to estimate these weights, and if you get poor estimates of the weights, it's not necessarily clear whether that will be more efficient than OLS. Again, remember, to do this, the optimality result comes from knowing the weights, and you can get exactly the right weights to transform the regression and make the Gauss-Markov condition hold. When you estimate them, they can be noisy, and therefore it may not hold in small samples. Another one is that the well, that's the main that's really the given that I'm not really else what sure you could put, because that for the in this question you know what the weights are. What is the main limitation of the W? Well, what did the solution put? I mean, I'm not. There's no other. I mean, it's that's the main one. The main limitation is that you don't know what the weights are in general. But of course, this question's told you that you knew what they were. So that'll be the main limitation, that you don't know the form of the weight, and you've got to estimate them in practice. Okay. So what about question tutorial 4? Wait. Yeah, 3. Yeah, we've done. This was from tutorial 3. Yeah, so we'll do tutorial 4. Okay, good. So sorry, tutorial 3. So we did quite a lot of these. We've got through quite a lot of this. So with this question 1, again, let's go back to tutorial 3. So question 1, we covered a lot in the second tutorial, so we covered most of that. So question 2 then, we can quickly breeze through some of the earlier bits just to reacquaint ourselves with the problem, but we did cover most of this. But there's a few bits at the end that we didn't have time to finish, so we can quickly run through this. So this is looking at the effect of price per citation, so the price of a journal relative to the number of citations, so a measure of the quality of the journal, on the number of subscriptions to that journal, controlling for the age of the journal and the number of words or characters in the journal piece. And it also allows this quadratic term on price per citation to allow a potential quadratic relationship between the number of subscriptions and the price per the citation. Okay, so the first we discussed the sign of the estimated set coefficients on PPC, age and character in this model. So we did this already. We went through this at length in the tutorial. So it's saying that for 1 unit increase in PPC, that subscriptions will decrease by, wait, it's measured in the number of, I think it must be in thousands, but it'll decrease by minus 0.08 or however many thousands. So it'll have a negative effect, which makes sense because as the price per citation increases, then they're in essence getting fewer citations for the money they're spending, so they're paying more on average for a lesser quality journal. So of course it's going to lead to lower demand. The age has a positive effect. You've got a positive estimated positive coefficient. Again, older journals tend to be the more established, well-known journals, so it makes sense that older journals have higher subscriptions, or which found in this example to have a positive relationship. And again, the characters could be a measure of the length. We're going to measure the length of the journal, so there could be more information in there, so it makes sense that that could have a positive effect, and that's what this is found in this sample with a positive coefficient. So what is the marginal effect of PPC on subscription? So all you just do is you just differentiate. You want to differentiate subscriptions with respect to PPC, and here we're going to get minus 0.98. So I'm going quite quick. We went through this in a lot of detail in the 0.098 PPC. And it makes sense. Now there's a non-linear. It's still linear in parameters, right? There's a linear parameter on each of these regressors, but there's a non-linear relationship between. There could be a non-linear relationship between subscription and price per citation. This is just saying then that the effect on price per citation is increasing slightly with the price per citation. So it's negative at very small, at low values of PPC. I mean, you're not going to get a price per citation of naught, but you can see it's negative for small values of PPC, and as PPC increases the price per citation, it's saying that the marginal effect of PPC on subscriptions is increasing or becoming less negative. So it's saying that the effect of price per citation increasing is not reducing demand as much for those journals with a higher price per citation. It would also say as well that as price per citation was large enough, eventually the effect of price per citation on subscription was positive. When this becomes positive, it just means the effect when this becomes positive, it means for that level of PPC, the marginal effect of an increase slightly above that is the sign of whatever this is. So when it becomes positive, then it's saying there's a positive marginal effect. So we can see the turnaround point where after PPC of 10, this will start to get higher. So the turnaround point is 10, namely it's the trough of the. If we got the subscription and PPC and draw it out, it will turn around at around 10. It's plotting. We can see the marginal effect as PPC increases. There's a decrease in subscriptions at a decreasing rate, and then eventually there's no effect at 10, and then it starts to increase. This says for PPC to 20, 30, 40 that there's a positive impact of PPC of price per citation on subscriptions, that they are actually getting higher demand. So we talked about this. So the next part, so D, to discuss the factors which would influence whether this quadratic specification is feasible, reasonable. Well, reasonable is a bit broad. Does it make sense? Well, if there wasn't any endogeneity here, if the model was well specified, we would expect that there should be a overall negative effect of price per citation on subscriptions, because we know that higher price there'll be a demand effect. On average, it'll lead to a lower demand. So we should expect for these to be negative. So the finding that we get positive effect of PPC on demand is obviously not really consistent with the economic theory here. But is then this reasonable? Well, it wouldn't really be. It's a bit of a broad question. If the model was correctly specified, it wasn't endogenous. Well, we shouldn't be expecting these to get these strong positive marginal effects of price per citation, especially at higher. Especially because it's saying here the effect as price per citation gets higher. There's a massive. It's saying the marginal effect of increasing price even at that level is having a huge increase in subscriptions. So we wouldn't expect there that for price per citation at some level, as it keeps increasing above that, demand would keep going up and up and up and up. It wouldn't make sense. But this is not necessarily consistent with the quadratic specification. Remember what we said, if all the price per citations we observe are 10 or lower, well then all the marginal effects in our sample would actually be negative, so that it wouldn't be inconsistent with economic theory. And we might not observe any, or there may not be many price per citation above 10. Because the citations tend to be in the thousands and the price not all that large. So it's usually the price per citation wouldn't really get above 10 anyway. Another thing is, well, is there evidence of a quadratic relationship? So you could view reasonable as is there evidence? And again, you do that by a t-test of the restriction that the true coefficient on ppc squared was not. And you can see the t-stat is around 1. So you wouldn't find evidence to reject the null at, say, the 5% level here, or even the 10 or 1%. So there's not really much evidence here to support the hypothesis, to reject the hypothesis that there is no quadratic relationship. Namely, we can't find evidence that there isn't much strong evidence that there is this quadratic relationship. In which case, this issue of the turnaround point would be irrelevant, because it would just mean that actually there's not really any evidence to support the fact that there is a turnaround point at 10. So that's another way you could see it. Another thing you could say is, well, it's actually likely here that the model is going to be, we're going to have omitted variable bias, or there's going to be simultaneity, because we know that the demand and the price are determined together. So it does actually make sense in this model, how it's estimated, that when price per citation increases, that demand will go up, because think of the most expensive, the better journals. For these journals, they're charging a higher. They've got high subscriptions. It's because they've got higher subscription that they can charge the higher price, or it's because they've got higher demand that they can charge the higher price. So actually, it's not unrealistic that you would find this in this model, because price per citation and subscriptions for some types of journals could move together. They could be a positive effect. And this would be the fact that we're not picking up the direct causal effect, but just how the two move together, and the demand and the price will always move to when again, as I said, that although the effect of change of all the effect of changing price from some given fixed level for some journal on average would lead to a lower demand. We're not observing that. We're observing the prices in equilibrium. So we know that the higher quality journals will have a higher demand, and they're setting higher prices just by their own definition. So we're always going to find that association. It's not that the price is increasing demand. As I said, it's the reverse. That the demand is higher and they can charge the higher price. So that, again, this question is again quite broad really, but it could make sense for it being in terms of it being a misspecified model where we've got a simultaneity. So E, calculate the R bar squared. So again, of course, you need to know the formula. So the R squared, which again, remember, is just the sum of explained squares divided by SST, is a measure of the amount of the linear variation, the amount of the variation in Y explained by the linear variation in the X variables. And in general, R squared can never go down. As you add in more variables, in general it will go up, but it can't go down. So of course we can't use that as a measure of model selection, because it would just say add as many regressors as possible. And we know that there's a degree of freedom loss. We can only add so many parameters. Let's say the sample size 10. You can't add more than 10 parameters anyway, and you would never set the number of parameters at or near your sample size, because you get a very noisy estimate. So you want to have as fewer regressors as possible, whilst making sure it's correctly specified, or it doesn't have a bias. So you can see there's this trade-off here, and that when we want to measure how well it fits, or how well a set of regressors fit to some data point, we can't use the R squared to choose the model. So we want to use an adapted model selection criterion. The R bar squared is one such criterion. It's a function of k, the number of regressors, the number of slope coefficients, and we can see now that when R squared increases, R bar squared will go up, but also when k increases, it will go down. So as you add in a new variable, k will go up, and in general R squared will go up, but k going up will reduce R bar squared, and r squared going up will increase it. So it's only going r bar squared will only increase if the r squared increases sufficiently relative to the increase in r bar squared from k going up. And what we can show is that this will add in a new variable. This model selection criterion will choose to add an extra variable if its t stat is bigger than 1. So that's what it does. In essence, it just chooses, it will include another regressor if its t stat is large enough. And remember, the bigger the t stat, the more likely it is that we can reject the null that the coefficient on that variable is not. But that just means there's some evidence to reject the null that there is no effect of that variable, namely that finding evidence that there is an effect, so that we want to keep it in the model. That's what it's doing. It's then just algebra, so you plug it in. So we get 1 minus, and then again we've got the r squared, so 1 minus 0. I can't read my handwriting now. Is that 853? Anyway, I forgot. It comes out. It's in the notes. It's 0.477. Then it asks you to do it again in this new regression. So in the next regression, it says that we've removed the quadratic term ppc square and included this interaction term age.ppc, and it's asked you to calculate the r squared again. And then again, so it's just the usual formula: 1 minus the r squared, which is 0.513 in this new regression, divided by the n minus 1, 179, which has got a sample size of 180, divided by n minus k minus 1. So we're going to get 175. Sorry, 17. Yeah, 17. Right, so we've got 4 variables. 5 with the constants, you're going to take away 5. So you've got the degrees of freedom is 175. Well, this is just 0.50. Is it 3? I can't remember my handwriting now. It's in the solutions. So it's asking you, did you expect r bar squared to increase or decrease? Well, because the sample size is the same in each of E and F, and because it's got the same number of regressors, because it's taken out one variable and added in one in, so in E and F, they both got the same number of regressors and they both got the same sample size. So all that can change in the formula is r squared. And so we can see here, we've got r squared over 179. And this is the same formula for each, 174. All we've got to plug in is the r squared, and the r squared is higher for F. So therefore we'd expect the r bar squared for F to be higher than in E. Okay, so if you're comparing, all this is saying is if you're comparing models that have got the same sample size and the same number of regressors, well then you just choose the one within those models with the highest r squared. It's because you've controlled all the models to have the same degrees of freedom. So in the trade-off then, once you've all got the same degrees of freedom, the best thing you can do then is to pick the model with the highest r squared, the one that fits the best for that given number of parameters for that sample size. Okay, so then for G, interpret the interaction term on age.ppc in this regression. Calculate and interpret the marginal effect of ppc on subscription. Okay, so we also did this in the calculate and interpret the marginal effect. Yeah, okay, so again, so now the marginal effect, going back to here, well now we want to find the marginal effect of ppc on subscriptions in this new model. So d subscription by d ppc, well just differentiate it, so you're going to get minus 0.961 plus 0.156h. So we can see now this is just saying that for small a for new journals there's a minus 0.061 effect of an increase in ppc on subscription, and as age increases the marginal effect of ppc increases or becomes more positive. So we can see after age of about 6 or 7 years, it's saying when this becomes positive after about 6 or 7 years onwards, that the effect of price per citation on subscription is positive. So it's saying for older journals, the more established ones, the more popular ones, that there's the effect of price per citation increasing actually increased subscriptions. So again, this could also be reflecting the bias. The older journals are the ones again that are going to be charging the highest prices, and they do so because they've got the highest demand to begin with. So this really suggests that the model's misspecified, because you wouldn't really expect there to be a strong positive effect of PPC on subscriptions. What it means is you found it in the data, so it's there. If you just do this regression with those variables, then it makes sense that you'd find that relationship, because for the older journals, well, their equilibrium prices are higher because they've got higher demand and the higher quality. So you would expect to find that the price per citation and demand would move together as from what you observe. But we want to get the causal effect of the price, and the way to do that would be, if you could do it, just to go out and you just change the price from, let's just say the market's in equilibrium, and then you just choose to change the prices of all these journals and then look at the change in demand. Well, that would get the causal effect, because it's not the price that's set in equilibrium, but you're choosing the price arbitrarily, and you can then see how demand responds to that. But you can't take the equilibrium price, because that obviously factors in the supply and demand together, and the higher quality, better journals are going to be charging more because they've got higher demand to begin with. So you're going to get this bias, this reverse causality. Okay, so it didn't actually, this again, part G didn't actually talk about that, but that's just it's actually to interpret it. You could actually, again, it's a bit broad, but if you interpret you'd have to say what it actually means. Namely, it's negative for new journals, and it increases, the marginal effect increases by 0.156 for every year in age. Again, you can also note here that this could be picking up the reverse causality bias. It wouldn't really make sense economically for there to be a positive effect of price on subscriptions for new journals, or for any journal, but especially for any journal. So assume that SSR, it should really say what the restriction is first, like to test whether so it's asking you to do a joint test that the coefficients on age and age.ppc are both not, against the alternative that one isn't not. And it's not actually specified in this case, and you have to in this case, given it's not specified a test, you can choose your own test. Let's just do a 5% significance level test. Well, so again, remember the formula. So in this particular case, you're going to have the H naught, we've got the unrestricted model, which in this case is going to be subscriptions on a constant, plus, now what is they included in there again? Let's just double check let's just write it out. Let's just write it out with a bit more detail so you see what's going on. So it's asking you, really, it should really say, it means do a test here from this model, where we're testing at the coefficient. So again, we've only got a constant and PPC, so alpha naught plus alpha 1 PPC. So let's just give a bit more detail, because the solutions are quite brief on this, plus alpha 2 age plus alpha 3 age dot PPC, plus the error term, call it U. Then our restricted model, well, the restriction is that alpha 2 equals alpha 3 equals naught. That the coefficients on age and age.ppc are naught. So this is our null, and our alternative then is alpha 2 doesn't equal naught, and or alpha 3 doesn't equal naught. So this is what we want to test. So the restricted model is just the model where we enforce the restriction. So the restricted model is just going to be alpha naught plus alpha 1 plus U. If the restrictions hold, well, of course these are both naught. It's going to simplify down. Okay, so we've got two restrictions here, and we're going to do we're going to set the significance level to 5%. It's not told you here, so you can choose your own and do your own test. So again, very important, because I'm seeing a lot of this mistake is you can only use a t-test to test one restriction. Here we've got two restrictions, so we're going to use the f-test. Remember, the formula is the sum of squared residuals from the restricted model, the one here, which has been given to you, minus the sum of squared residuals when you run the unrestricted regression here. Again, that's given in an earlier question, divided by, so I'm giving the general formula Q, it's the number of restrictions under the null, again, the restrictions could be anything. They could be set them to 0 or 1 or 5, doesn't matter, but it's a number of restrictions that you've got. There's 2 restrictions here, divided by the sum of squared residuals in the unrestricted model, divided by the degrees of freedom in the unrestricted model. And you don't need to remember the n minus k or n minus k minus 1. It's easy. It's just n sample size. The degrees of freedom is n minus the number of parameters estimated. So it obviously includes the constant. So we've got 1, 2, 3, 4 here. So the degrees of freedom then is just going to be n minus 4 here. That's the number of that's sample size minus number of parameters. So that's the formula, and this here turns out for n large enough to be distributed f with q degrees of freedom and d degrees of freedom unrestricted model UR in general. Okay, so we've got to work on our question. So we're being told that the sum of square residuals in the restricted model is 5, 6, 8, 8. So in our case, we're going to have 5, 6, 8, 8 minus, well, you're given the sum of square residuals in the other model. It's 4, 6, 6, 6 from the unrestricted model. And remember, it makes sense. The unrestricted model is more flexible, so that it's in the unrestricted. The SSR from the unrestricted can never be bigger than the SSR from the restricted. When you enforce the restrictions, then the SSR in general will increase because you've got fewer variables to explain the variation in y. And again, if the restriction, if the alternative is true and these are actually not, well, we can see that actually the sum of square residuals can often be a lot lower in the restricted one because we've missed out these 2 variables that are explaining some of the variation in y. So if alpha 2 and alpha 3 were big, well, actually the sum of square residuals will be much bigger in the restricted relative to the unrestricted, and that's why we look at the difference between these two, because under the null these things should be on average, I mean they're random variables, but they should be quite near to each other. Okay, so that's kind of the intuition behind what's going on with the test, divided by number of restrictions. So in this case we've got 2, and again it makes sense that you divide, because when you've got this sum of square residuals, and again it's random variable, but as you increase the number of restrictions, well, when there's 10, 20, 50 restrictions, there's more chance that there could be a larger deviation from these 2 because you've got more variables that you're omitting. So there's more. So you divide by q to kind of normalize that. That's what's going on there. So then we divide. So we've got sum of square residuals in the unrestricted model divided by the degrees of freedom. So this is going to be 175 here. We've got 5, 1, 2, 3. Have I missed? There's also character as well. Sorry, that was there. I didn't see that. So there's 5, right? Because there's plus. There's also the character. So it's going to be n minus 5. Sorry, it's spread over the next page. So we're going to get 175. Which is 5.7, I think it's 3, is it? But check the solution. So then that's our test statistic, and we're doing a 5% test. The critical value is 3. So the test statistic is bigger than 3, so therefore we find evidence to reject at the 5% level. Okay, and remember, it makes sense that if the null isn't true, the bigger should be the difference between the restricted and unrestricted sum of square residuals after we scale by the number of restrictions that we've made. So this is saying that they're quite far away from each other, and this is saying that actually that observing the difference between the restricted and unrestricted sum of square residuals is just not likely to happen if the null was true. It's saying that actually it's likely that the null isn't true, and that's why we're finding very different residual sum of squares in each model. So then 3 is in our 5% critical value from the F distribution. So we've got the F distribution looks something like this. So this 3 will leave us with 5% in here. So of course, in our case, the test statistics over here. So it's well into the rejection region. So this would be the rejection region. This is 3. the critical, then we get 5% here. So our test statistics over here. So we're in the rejection region. It's just saying it's too unlikely. It's saying at the 5% level, it's just too unlikely that we would have observed a F stat this large if the null was true. And so it's always the same idea when we're doing a test. So the last bit that's nearly done is reparameterize the model to make it more sensible. And then J, we've already done something similar to this in an earlier question. This is the last bit, key bit. Well, make it more sensible is a little bit broad. What it's getting at is that in these models, when you've just got, let's just focus on the bit with the age and the reparameterization. So we'll run through this, what it means. Again, sensible is a bit broad. What it's getting at is, well, when you want to look at working out marginal effects in these interaction term models, well, it's not as straightforward as when we don't have these interaction effects. Namely, the marginal effects depend upon the level of another variable now. So in this model, we've got, just focusing in on the bit with age and subscriptions, we've got, let's just do it in the general case, alpha naught plus alpha 1, the coefficient on, say, PPC, plus alpha 2, the coefficient on age, and then plus, then have alpha 3 age dot PPC. Again, plus, we've got these other terms, we've omitted them up. This is just a bit of interest. We want to look at the marginal effects of PPC and age. Well, here, for example, we can see then the marginal effect, let's just do it on P, we've already we can see here, it's just alpha 1 plus alpha 3 times age. So now, the effect of PPC on subscription, the marginal effect, this, when alpha 3 doesn't equal naught, is a function of age. So therefore, there isn't just one marginal effect now. If alpha 3 is naught, namely there's no interaction effect, well, in that case, the marginal effect is just constant. It's just alpha 1 for all people of all ages and all characteristics. When alpha 3 doesn't equal naught, well, it depends on the age. So there isn't just one marginal effect. There's one for each age level. So then it's a matter of which one do you want to report. And we're often interested in looking at the marginal effects around the mean, because that's going to represent the average person. So normally, then, all this, we want to reparameterize this to then rewrite this as deviation from its mean, as opposed to the level. And all that will then do is just retransform this. So then, when we transform this to be in the deviation of its age from its mean and PPC from its mean, it's going to retransform the regression such that the new coefficients on PPC and age will reflect the marginal effects at the mean. So that's kind of what we want. We want that, which is not an issue when alpha 3 is naught, we can drop that out. Well, alpha 1 and alpha 2, they'll be the marginal effects at the mean or anywhere. But when alpha 3 doesn't equal naught, of course, the marginal effects depend on age and PPC. So we want to then just reparameterize it so that these coefficients on PPC and age reflect the marginal effect at the mean. So all we do is just add and subtract so we can do it then. So let's go back and rewrite it. Subscription alpha 1 well, we want to add and subtract, want to subtract the mean out from age. So subtract the mean of age minus, call it mu of A. Well, to do that, again, times PPC. We've got to keep it consistent. We're going to have to add alpha 3 mu A PPC. Right? All we've done is added and subtracted this mu A, mean of age, times PPC. So then it balances back out to the above. This will collapse back down to this. Again, we can forget about the other. We're just comparing the bits that just relate to the age and PPC. These two, this will then be equal to this. We just subtract out the age and then add it back. It's going to get times by PPC. Right? You then do the same for PPC. So you subtract its mean from within here minus the mean of PPC, call it mu P. and it's got to balance out. So you've got to add on everything that you've just taken away. So we've taken away mu p times alpha 3 times all of age minus mu a. That keeps it then balanced. So these, again, they're all equal, they're all equivalent to each other. So we're getting there. We've now got this last part, this interaction term now, and its deviation from its mean term. So if age and or PPC are at its mean, this becomes naught, and it just measures then the change when from age and PPC going above or below its mean. Well, that's going to then, we can then rearrange this. This is now going to change the coefficients on these age and PPC. So we can see this from here. So if it's, we can see that this alpha 3 mu a PPC is going to come to here. Then we can expand this last part out. So the first bit is we're going to get alpha naught plus alpha 1 plus alpha 3 mu a times PPC. So that's now our new coefficient on PPC, which we can see just the marginal effect at the mean, because again the marginal effect of PPC depends on age now. So this is just evaluating at its mean. And then if we expand all this bit out, well, we can see we're going to get plus mu p a3 age. So we're going to get plus alpha 2 plus mu p alpha 3 a. And then we're going to get this minus mu a mu p a3. That's going to come over here. So we're going to get minus mu p mu a alpha 3. And that's it. And then plus this alpha 3 age minus mu age times PPC minus mu PPC. And that's it. So all we've done is shown that we can rewrite this equation as equal to a constant, call it B0, plus B1 age, PPC, sorry, plus B2 age, plus B3, and then this age, this effect and its deviation from its mean form, where we can just compare the coefficients. So B0 is of course alpha naught minus this mean term, mu p mu a alpha 3. B1 is just this coefficient, and you can see that this is just the marginal effect of PPC on age at the mean. This again, the mean here, this we know that the marginal effect of PPC on subscription is a function of age. So this here is just evaluating at its mean, and the same for PPC evaluates that at its mean. And again, now the marginal effect of age is going to depend upon PPC, alpha 2 plus mu p alpha 3, and then B3 is just alpha 3. So writing it in this way, well, now this last term is not when either age or PPC are at the means. So these B1 and B2 reflect the marginal effects of age and PPC at the mean. So that's often why we sometimes report it in this way. It's not an issue when there are no interaction effects, as I said, because the marginal effect is just the same for any level of the variable or any of the other variables. You don't need to do this. But in this instance, often researchers are often interested in what's the marginal effect for the average person. So we often write it in this way, and that's all that this has done. Okay, so we'll leave it there. And so if again we can do some more over revision week or onwards. We could do some past exam sessions. So again, I might do a poll, or I'll run a poll and see if any of you want to see which question.